Hey guys, what's up? Eddie Aho here with KissAnalog.com. Alright, so today is an introduction to SPICE. We want to talk about where it came from, what it's good for, what it does, and how to use it. And we're going to cover a lot, so I'm going to go fast. Let me pull up my first board. Okay guys, this is another installment in the Kiss University series or playlist, links below. That's where we mean to take you from basic DC electronics all the way up to advanced engineering. You know, series parallel circuits we start, that kind of thing, and bring you all the way through. So, the introduction to SPICE belongs there, right? Now, a lot of times we call it Berkeley SPICE, because if it's not Berkeley SPICE, it's not a true SPICE program. It might be a simulation program, but it's not based off Berkeley SPICE. If it is based on Berkeley SPICE, then you kind of know what to expect, because you know how Berkeley SPICE works and how it's made, and we're going to talk about that, okay? But Berkeley SPICE came from Berkeley University in California, United States, and the driving force behind that was this Dr. Donald Pedersen. Okay, they call him Don, and he was studying transistors back in the early days when they, when they first came out, and they're trying to study them and understand how to do the math and all that kind of stuff behind them. Well, at the same time, he came from industry, from what I understand, went back to teaching, and he got into computer science program, in that part of the school. And they started writing programs to understand how to do the equations around the transistor, okay? So he got involved trying to understand the transistor and doing the equations and computer programming for that, and they wrote some programs and they were really successful at that. In the 1960s, he actually developed an IC fabrication lab at the university. A lot of people in the industry, other universities, thought he was nuts. They didn't think it was possible to do that at a university, but he did. And so it helped that university develop a lot of work, because they could actually fabricate what they're doing and prove their concepts. Well, when the JFET came along, the thermal issues with that, with biasing and such, added another complexity. So they wrote a program called BIAS, and that was also successful. Then another couple of programs were written to do other things. Well, this Professor Dr. Ron Roher, what he wanted to do was come up with a simulation tool that kind of encompassed everything. So he had his students break up into teams, and each team took on a part of that program. And then he had Don select which team did the best job on what particular part of the program they're writing. So they came up with cancer, and it was very successful. Problem is it was paid for by industry, and so there's an IP thing, an intellectual property thing that was owned by the industry. Well, Don didn't like that. He wanted something that the engineering community could use. And so I think Ron Roher ended up leaving the university, going back out in the industry, and Larry Nagel was one of his top guys, Dr. Larry Nagel, who I believe later on became the dean of the department. Well, anyway, he worked with Don, and in 1972 they released SPICE 1, the first version of SPICE. And SPICE stood for Simulation Program with Integrated Circuit Emphasis. Okay, so he got what he wanted, and now they had a tool that was good at simulating circuitry with transistors and diodes and FETs and things like that. Okay, and it was open source. That's also what he wanted. So he really should be given credit for helping advance technology, because without that, I mean, the math, other ways to do it using math and spreadsheets, it would have been very difficult to build an IC with hundreds, if not thousands, of transistors, or tens of thousands of transistors in them, without being able to solve those circuits quickly. So yeah, that's how it started. That's why it's called Berkeley SPICE. And let's talk more about that. Okay, so what does SPICE do? What does it simulate? Well, I kind of made a list here of the main simulation tools built into what they call it. They kind of call SPICE a general purpose simulation tool. Nonlinear DC analysis. Nonlinear transient analysis. That's probably the one I most commonly use. And then linear AC analysis. That's like Bode plots, that kind of thing. Now your DC analysis, usually what happens before you run one of these two things, the program will set up the DC characteristics. You might have, say, a capacitor that's going to have an initial condition that's going to be charged at 100 volts. So it goes and looks at all that stuff, sets up the circuit before it runs these two things. So even if you're not doing this, it's kind of doing it in the background, okay? And then I put these in red because these, I believe, came secondary. Pole zero analysis, you know, your transfer function type stuff. Small signal analysis, small signal, not power stuff, you know. And sensitivity analysis. Okay, that one might not be obvious, but because some SPICE tools don't have these things. They, you know, they cost extra to get that level of program that includes these parts of the program. I believe MicroCap has all this stuff and more. Okay, but sensitivity analysis, when you change one value of one part, let's say the tolerance of one part is critical, because if it changes just 10%, it affects the output by, say, 30%. Other parts can change by 20% and they change the output very little. So that's what you do with sensitivity analysis. Find out what parts of your circuit are very sensitive. If you find one that you didn't expect to be, you know, cause that kind of sensitivity, you can do things to change that if you can, you know, but at least it gives you an idea of what to look for. Make that a 0.1% resistor if you had to. But anyway, noise analysis. Every part, even a resistor, is going to have some thermal noise or some, you know, noise associated with it, JFET or whatever. So noise analysis helps you study that. Also, like if you're doing like THD, stuff like that, you can do some analysis with that. So these are the most common ones, okay? So that's what SPICE will do for you. All right, our next board, it shows how we build those circuits. The circuits are built by these things and some other things too, but this gives us an idea. This is not an all-inclusive list and that, but I'm trying to give you some examples of how the circuit's built. Some things are simple elements like resistors, capacitors, inductors, and when you put those on your schematic, like for instance a R, it needs to be named with the R. Starts with the R. Doesn't really matter what the string says after. It could be R1, could be something like that. R123 XY. Doesn't matter what the string is, as long as it starts with the R. So you might want to call R load, like your load resistor. Okay, but it has to start with the R. You can't go load resistor. Okay. The next level are a little more complex, like transistors, semiconductors, basically. These are usually two-lead devices. These are not always, but usually a diode's two-leaded, but still it's a semiconductor. Now, these things also can have more levels of complexity called levels. And you can have a transistor level 0 or level 9 or even more. I think MicroCap has many levels. Depending on how deep you want to model that transistor, the thermal junctions and capacitances and all the things, all the elements that are inside that transistor, you can go to different levels. Now you might say, well, I want to have the most complex level every time so I get the most correct, you know, simulation. The problem is you could slow down your simulation if you have a whole bunch of parts and you're going to level 9 on everything. So some things can be more ideal. They won't really change your circuit behavior, and so you can choose your level, okay? The next level of complexity is subcircuits. Subcircuits usually start off with an X, and subcircuits can be combinations of all these things, and they can even have other subcircuits in them. So you can take a whole schematic and make it a subcircuit and put that into your next simulation as a subcircuit, okay? So subcircuits can be very complex. So obviously, you know, that can really slow down your simulations if you have gigantic subcircuits. But like an op-amp, an integrated circuit would be a subcircuit, okay? Another thing I should have put down here as a list is your voltage sources, because that's another necessary part of your circuit. And the voltage sources can be independent voltage source, like a 12 volt battery, 12 volt DC source, called a battery if you want. Or it could be so that would be called an independent voltage source. And then there can be dependent voltage sources. And dependent would be like, okay, if I have this voltage here, I'm going to have X voltage here. Or you can have dependent and independent current sources. Okay, so I should have put that as another one of the main parts of the board. I just thought of that as I'm sitting here. All right, okay, let's go to the next board. All right, guys, so this is a schematic, just kind of showing how you would do it. Back in the day when Berkeley first came out in SPICE, it was different. It's not like today where you had a schematic in, where you put your schematic into the computer. Back then, you had to put your, here, let me just kind of walk you through it and tell you what you do. You'd take your schematic, you put it on a piece of paper. You'd go around and you'd number the nodes. And so you would say, so this is a branch, they'd call it, and you'd say, okay, this is going to be 0. That's my ground. That's my reference point. And the program's going to know that a 0 is your reference point. Then you number each one. So I have a 1 here and a 2 here. I could have numbered this any number I wanted, but anyway, you come up with your numbers like this, okay? Then after that, you have to write down your circuit. So then you would draw a list of your schematic in a nodal list, and it would look something like this. These are your nodes, okay? And each one of these is a branch, and you have your elements connected to your branches. And so you'd write them down into like a program list, and you'd follow the syntax for each one of these things. The VCC, first you'd call it V, and then it could call it anything, but say CC for instance. And then this first place would be this node, and then this node, and then this value. And then there might be some other things that you could put in there, like temperature, things like that, but you'd put the syntax down like that, okay? And then you'd go to your resistor, or the next element in your circuit, and you'd say, okay, that's connected between 1 and 2 nodes, and it's 1 mega ohm. Now, I could have put down some other parameters in this statement too. Like one of them was temperature. So I might put 27 degrees or 50 degrees C. And I think it was in Celsius. Okay, so then C1 is connected to 2 to 0. Now again, R could have been RX or R load, and C, Y, whatever, but it has to start with V, R, C. Then I say it's connected between 2 and 0, and it's 1 micro. Now meg, it was that you had to go capital MEG because there's milliohms, and that program didn't decipher between a capital M and a small m. It wanted to see MEG, capital MEG, so there's no ambiguity between the two. It was for certain meg. And then at the end of your list, your nodal list, you'd have this end statement. So the program would say, oh, here's the circuit, and it'd run the circuit. Now you can imagine if there's a transistor in here, it'd say Q, it'd start with the Q, and then it'd have 3, because it's a 3-pin device, so it'd be 2, 0, 1, let's say. And then it would be, and then after that, because it's a model, it would say model, like Q model, and then it would have, in that Q model, there'd be a whole list of statements like this, what's inside that Q model, okay? Sub-circuit would even be more complex. But, so to write down your circuit this way, back in the day, shows you how long I've been around, I used to do it this way, and man, you would, if it didn't run smoothly, your simulation didn't run, you'd have to go back and see where your syntax was wrong, where you made your mistake. It was pretty laborious. So when companies came out like MicroCap that offered the interface to the Berkeley SPICE, that's what makes them different. Intusoft was one of the first ones, MicroCap, SPICE, you guys probably heard of that. That was de facto industry standard. Everybody knew PSpice back when I got started. It was just a thing. It was just one of those programs that it was bought up by another bigger company, and it was kind of swallowed up. It kind of lost its identity. I think they lost their foothold in the SPICE world with engineers, because my first few companies I worked for, every one offered PSpice. And still, even more recently, I've had companies offer PSpice. In a huge company, they might only have 2-3 seats because it just lost its popularity. And personally, I feel like PSpice, the interface to PSpice, has just gotten to be burdensome. It's just not easy to use. MicroCap is one of the easiest ones to use. Okay, now a lot of you guys are probably familiar with LT SPICE. It's been a free program for many years, and that's why the popularity. Hey, free is good, right? Part of that you have to remember is that there's a company, LT, selling their parts, that they didn't want to share the guts of their parts. And so, like say Texas Instruments had TI or TINA SPICE, and that's a free one too. But they didn't push that much. You know, it's, hey, it's on your website if you want it, but they would give the SPICE model to you, and you could use it in any tool you wanted. You know, they didn't try to put their arms around it and say, you can't see inside our stuff, you have to use our tool. So LT kind of controlled what, you know, is inside their stuff by giving a tool, a simulation tool to you. And so in the early days it was based on Berkeley SPICE, but it hasn't been based on Berkeley SPICE for a long time. It went to some kind of matrix math model. And really the idea behind LT SPICE is they want to do simulations fast. That's what it's about. And it's all about putting their parts into circuits and simulating their parts. When I showed that circuit, when I was showing models and all that stuff, you know, the simple element, the model and subcircuits, well, there's another thing, another part of that is a type of model that's behavior model. And so you know, you might have 10 pins into an IC, and you say, well, if I have this clock coming in here, I'm going to put this out here. And what goes on inside that could be very, very simplified. Like when I was talking about transistors and all the levels, well, the parts that are in LT are pretty much like push this button, and you're going to get this output. It's just going to happen that way. And so they just wanted it to... One of the problems with SPICE is in the early days, you know, not too long ago, until the computers got really powerful, it would take a long time to run a simulation. And another thing that would happen is, you know, when I pointed out those nonlinear analysis means that all of a sudden you take a step function. And when that happens, the math and everything can go in la-la land. And the SPICE would just come to a screeching halt, and it couldn't converge. A lot of times you get these convergence errors because it's trying to converge to a point and it just goes like, you know, to infinity or whatever, and it doesn't converge. So that was one of the common problems. Well, LT SPICE kind of solved that by simplifying the models, and so you get real quick simulations. But I don't know. I think you might have to question some of those simulations. Anyway, it's a free tool, and it's usable. And if you're not using their parts, it'll model transistors. It'll take a lot of the SPICE models and actually, you know, it translates them into their own thing. But anyway, that's just a little thing on LT. Don't give me a thumbs down if you're an LT lover and you hate what I just said, but that's just the way it is. So Berkeley SPICE is nuts and bolts. You might have a convergence error. There's some things which gets more complex, we'll cover that later, that if you do have those kind of problems, there's some ways to get around the mathematics. So anyway, we'll cover that stuff later, but this kind of gives you an idea of how the SPICE works and why this ground. So when you're put a schematic into, say, MicroCap, if you don't put a ground symbol in there, it's going to have a problem, and it's going to tell you right away. It's going to say, hey, I don't have a reference point. So you need to put that ground symbol somewhere in your circuit. Doesn't really matter where. It doesn't have to be truly ground wherever you think it is. It just has to be whatever SPICE does is it's going to look at your circuit, and wherever you put this, it's going to call that node 0. It's just going to name that as node 0, and it's going to base the analysis on this. So when you take your probe and you click it up here, it's going to tell you the voltage between here and node 0. So that's kind of the introduction of where SPICE came from and how the circuits are built, and why MicroCap and Intusoft and SPICE programs like that make Berkeley SPICE a lot more usable and easier to use, because you don't have to do this. Now on Berkeley's website, they do have the SPICE and the latest SPICE, but they also have an interface, and it's been years since I've tried to use that interface, but it's not going to be like MicroCap. It's not going to be as dressy. As a matter of fact, LT SPICE, you guys, if the LT SPICE guys will actually download MicroCap and try it, you'll see, I think won't be too long before you'll be using MicroCap, but the interface on MicroCap is just very nice. That's why they sold it for $4,700 up until they decided to give it away for free and retire. Lucky us, right? Okay, so if you haven't downloaded it yet, links down below, and links below for the series. Okay guys, this has just been a quick intro into SPICE, or Berkeley SPICE, and I'm going to show you kind of the old school way of how we had to do things before companies like MicroCap and Intusoft and SPICE came along and offered the interface. Now what I'm going to do in the next video is I'm going to show a real introduction into MicroCap, starting from the basics. Okay, we're going to build a circuit, something like this, and we're going to make it really simple. Okay, so hopefully this is something that you guys can follow. Let me know what you guys think, and let's just talk about this slide. Alright guys, hope that was helpful. Hope that kind of helped, teach you something about MicroCap and the basics about how it works. And it's just a quick intro, okay? So give the video a thumbs up if that was helpful. That helps the video a lot and helps the analytics, and when YouTube thinks people like it, then they share it with other people. So alright, thanks guys for watching. See you next time.